The nearest star beyond our own sun has a name that almost sounds like a comfort: Proxima Centauri. And that word, proxima, meaning nearest in Latin, has been quietly misleading people ever since astronomers first attached it to that faint red point of light in the southern sky. Here's the thing most people don't realize. Nearest doesn't mean close. Nearest means least far. And in the context of interstellar space, those two things are not even remotely the same. When we call Proxima Centauri our nearest stellar neighbor, we're using the word the way an astronomer uses it, relative to a scale where everything is incomprehensibly far away. It's the shortest distance on a list where all the distances are catastrophic. That's what nearest means out here. Not accessible, not reachable. Just the least impossible option on a list of impossible options. Proxima Centauri sits in the southern sky, invisible to the naked eye. You cannot see it without a telescope. Despite being the closest star to Earth outside our own solar system, it's too faint, too small, too dim to register for human eyes under any conditions. Magnitude 11.13, which is approximately 100 times below the threshold of what an unaided human eye can detect on a clear night. Our nearest stellar neighbor is a star we can't even see. That should tell you something right away about what kind of neighbor we're dealing with. What's doing the psychological work here is the word itself. Proxima, nearest. It carries an implication of proximity, of something within reach if you just tried hard enough. We're used to nearest meaning something navigable. The nearest gas station, the nearest hospital, the nearest city. Those are things you can get to. You might have to drive for a while, but you get there. The word nearest has always implied reachability, and we carry that assumption directly into astronomy without realizing it. The reality is that the distance between us and Proxima Centauri isn't just large in the way that, say, the distance across a continent is large. It's a different category of large entirely. It's large in a way that breaks the intuitive systems your brain uses to estimate distances and travel times. Human beings evolved to navigate a world measured in meters, kilometers, maybe a few thousand miles at the extreme end. We are not equipped at the level of gut feeling to comprehend what 4.24 light years actually represents as a physical distance. This isn't a failure of imagination, it's a hard limit. The numbers involved are so far outside anything our ancestors ever needed to process that no amount of concentration will make them feel real in your chest. You can say the number. You can do the math. But you cannot feel it the way you feel the distance between two cities. That gap between knowing and feeling is exactly what we're going to spend time with tonight. Proxima Centauri is a red dwarf, a small and dim star, part of a three-star system called Alpha Centauri. It has planets. One of them sits in what astronomers call the habitable zone, the range of distances where liquid water could theoretically exist on a surface. The discovery of that planet in 2016 electrified researchers and the public alike. Our nearest stellar neighbor wasn't just a star anymore. It might be a destination. It might harbor conditions relevant to life. People started talking about it the way you talk about somewhere you might someday visit. That framing is part of the problem. Because the question of whether we could ever actually get there is one of the most humbling problems in all of science and engineering. Getting to Proxima Centauri isn't a matter of building a bigger rocket or waiting a few decades for better technology. The challenge runs deeper than that, down into the physics of energy, the limits of human biology, and the brutal arithmetic of what speed means when the distances involved are measured in trillions of miles. Tonight, we're going to look at that distance honestly. Not the version that sounds exciting in a headline, but the version that tells you what it would actually cost. And by the time we're done tonight, The distance between us and that star is going to feel like something entirely different than a number on a page. Let's start with the actual number, because the number is where most people's intuitions quietly break down. 4.24 light years. That's the distance to Proxima Centauri. Most people hear that and think, okay, that's a unit of distance, that's far, and then they move on. But the number deserves more than that. It deserves to be taken apart piece by piece, because once you actually do the math, something shifts. It stops sounding like astronomy and starts sounding like a problem. So let's build this from the ground up. A light year is not a unit of time. That's the first thing to get straight. It's one of the most common misconceptions about the term. A light year is a unit of distance, specifically the distance that light travels in 1 year. And light moves fast. It moves at about 300,000 kilometers per second. That's not 300,000 kilometers per hour. Per second. In the time it takes you to blink, light has already traveled roughly 300,000 kilometers in 1 second. Let that settle for a moment. At that speed, light circles the entire Earth about 7.5 times in a single second. It travels from the Earth to the Moon in about 1.3 seconds. From the Earth to the Sun takes roughly 8 minutes. These are the numbers astronomers use to give light speed some grounding, and they're useful. But they're also where the intuition starts to fail, because nothing in daily human experience moves at anything close to this speed. We don't have a reference point. We're working with a number that has no natural analogy in the physical world we grew up in. Now multiply that speed by a full year, 365 days every second of every day, and you get 1 light year. 1 light year works out to approximately 9.44 trillion kilometers, or about 5.88 trillion miles. That's 1 light year. 1. A number so large that it's essentially meaningless in everyday terms. This is exactly why astronomers invented units like the light year and the parsec in the first place. When you're dealing with cosmic distances, kilometers become absurd. You end up writing numbers with so many zeros that the figure loses all informational value. The light year exists because it compresses that absurdity into something you can at least say out loud without losing track of the digits. Proxima Centauri is 4.24 light years away, so take 9.44 trillion kilometers and multiply it by 4.24. The result is roughly 40 trillion kilometers, about 25 trillion miles. That's the actual distance between us and the nearest star. 40 trillion kilometers. The number is technically readable, but writing it doesn't help. It's the kind of figure that looks like a phone number that got out of control. There's no human context in which 40 trillion kilometers means anything at all. You can't compare it to a road trip or even to the diameter of the solar system in any way that gives it real weight. The solar system itself, out to the edge of the Oort cloud, is roughly 2 light years across, and even that comparison reveals the problem, because 2 light years is still an incomprehensible distance. Here's where things get uncomfortable, though. The raw size of the number isn't even the strangest part. When you look at Proxima Centauri through a telescope, which you'd need because it's far too faint to see with the naked eye, you're not seeing the star as it exists right now. You're seeing light that left Proxima Centauri more than 4 years ago. The light traveling through space, covering 300,000 kilometers every second, still takes over 4 years to make the trip. By the time it reaches your eye or your camera lens, the star you're looking at has already moved on. It has burned through 4 more years of hydrogen. Any flares it produced in the last 4 years haven't reached us yet. Any changes in its brightness, any new phenomena, we won't know about them for years. You are, in a very literal sense, looking into the past. This isn't a metaphor or a poetic way of framing it. It's the physical reality of how information travels through space. Nothing moves faster than light, so no information about Proxima Centauri can reach us faster than light can carry it. The image of that star that exists in telescopes and photographs and textbooks right now is a 4-year-old image. The star we've been studying and measuring and naming planets around. We're always seeing it with a 4-year delay built in. If something dramatic happened to Proxima Centauri yesterday, we won't find out until the year 2029. Most people don't sit with that long enough for it to actually land. The delay isn't a technical inconvenience or a minor asterisk. It's a fundamental feature of what it means to observe anything across these distances, and it gets worse the farther out you look. The sun, which is only about 8 light minutes away, we see as it was 8 minutes ago. Sirius, the brightest star in the night sky, is 8.6 light years away. That's a delay of 8.6 years. The Andromeda Galaxy is 2.5 million light years out. When you look at Andromeda, the light you're seeing departed 2.5 million years ago when early humans were still making their first crude tools. Proxima Centauri, at 4.24 light years, is actually on the very low end of this delay. It's as close as it gets, and even here, the gap is more than 4 years. That 4-year light travel time is the baseline number this whole conversation builds on. Every question about reaching Proxima Centauri, every proposed spacecraft, every propulsion system, every theoretical mission gets evaluated against what light can do, because light is the fastest courier the universe allows. Light, moving at the fastest speed anything in the universe can travel, takes 4 years and 3 months to make that crossing, and that's the benchmark everything else gets measured against. Here's one way to feel it in your chest. If you could walk in a straight line through the vacuum of space at a normal human pace, the journey to Proxima Centauri would take approximately 950 million years. Not 950 years. Not 950,000 years. 950 million. The first complex animals on Earth appeared roughly 600 million years ago. You would not even be halfway there yet. That number is so large it stops functioning as a number. So let's try a different unit of measurement, one that feels more like a human achievement. The Apollo missions represent one of the most extraordinary things our species has ever done. The spacecraft that carried astronauts to the moon reached speeds of roughly 40,000 kilometers per hour on the return trip, fast enough that for a few minutes, they were the fastest humans in history. Point that same spacecraft at Proxima Centauri, and the journey takes about 43,000 years. Agriculture was invented around 12,000 years ago. Writing appeared roughly 5,000 years ago. The Apollo spacecraft, our symbol of everything human ambition could accomplish, would need nearly 4 times all of recorded history just to reach the nearest star. Maybe Apollo feels too old. Let's use something more recent. Voyager 1 is the farthest human-made object in existence. Launched in 1977, it has been traveling continuously for nearly 5 decades and is now well beyond the edge of the solar system, moving through interstellar space at about 17 kilometers per second. That is genuinely astonishing. At that speed, it would take Voyager 1 over 73,000 years to reach Proxima Centauri. The last time humans were doing anything 73,000 years ago, we were surviving the aftermath of a catastrophic volcanic eruption that may have reduced our entire population to a few thousand individuals. New Horizons, the spacecraft that gave us our first close-up images of Pluto in 2015, is moving even faster than Voyager at around 58,000 kilometers per hour. it would take approximately 80,000 years. That's further back than the earliest cave paintings. Further back than any human civilization, any language, any tool more sophisticated than a sharpened stone. Here's where things get uncomfortable. Those are our old spacecraft. What about our fastest? The Parker Solar Probe, launched in 2018, is the quickest vehicle humanity has ever built. At its peak velocity, achieved by falling toward the sun and using its gravity to slingshot around it, the Parker Solar Probe reaches approximately 692,000 kilometers per hour. Traverse the continental breadth in roughly 6 seconds. It is breathtaking. It is a genuine engineering marvel, and if you pointed it at Proxima Centauri, it would take roughly 7,200 years to arrive. 7,200 years. The Great Pyramid at Giza was completed around 4,500 years ago. The Parker Solar Probe, at the peak of everything we know how to do, would need more time than separates us from ancient Egypt, and then some, just to reach our nearest neighbor. The Parker Solar Probe's extraordinary velocity helps illustrate the fundamental constraint we're working against. Even traveling at nearly 3% the speed of light, it still requires millennia to cross interstellar distances. Light itself, the fastest thing in the universe, takes over 4 years to journey from Proxima Centauri to Earth. This isn't a limitation we can engineer around with better rockets or more efficient fuel. The vast emptiness between stars isn't something we've failed to overcome through insufficient effort. It's a feature of the universe itself, a consequence of cosmic scale that predates human technology by billions of years. These numbers aren't telling us we need superior spacecraft design. They're telling us the problem may be fundamentally different from what we normally solve. There is a scale model that makes the geometry of this slightly more graspable. Imagine shrinking the solar system down so that the distance from Earth to the Sun is exactly 1 inch. At that scale, you could hold the entire inner solar system in the palm of your hand. Jupiter would be about 5 inches away. Neptune, the outermost major planet, sits around 30 inches out, just under 3 feet. Now, at that same scale, where is Alpha Centauri? About 4 miles away. Not 4 feet. 4 miles. A long drive, not a short walk, and that's in a model where the entire Earth-to-Sun gap has been compressed to the width of your thumb. Even in a version of the universe deliberately scaled down to make distances manageable, the nearest star is still over the horizon. What's striking about all of these numbers, the 950 million years on foot, the 43,000 years by Apollo, the 73,000 for Voyager, the 7,200 for our absolute fastest, is that they don't cluster around a single order of magnitude. They vary by a factor of more than 100, and yet every single one of them still lands somewhere between deeply discouraging and completely impossible. You can improve by a factor of 10, improve again, and the answer is still measured in millennia. The ceiling we keep bumping against isn't engineering, it's physics. It's the sheer quantity of empty space between us and anything else. There's a temptation when confronted with numbers this large to round them off emotionally, to decide they're all basically the same flavor of impossible and move on. But there's something worth sitting with in the specific shape of the problem. We are not close to a solution and then failing to execute. We are not a modest upgrade away from being able to do this. The fastest thing we have ever built needs 72 centuries. The spacecraft we use to reach the edge of the solar system needs 73,000 years. These are not engineering refinements apart from each other. These are entirely different categories of capability. And remember, this is the nearest star, the closest one. The one astronomers named Proxima specifically to indicate its proximity, and we're talking about tens of thousands of years with our best hardware. The question of how we know the distance, not approximately but precisely down to the fourth decimal place of a light year, is actually one of the more elegant stories in astronomy. It starts in 1838 with a German astronomer named Friedrich Bessel, and it starts with a trick so simple you've been doing a version of it your whole life without knowing. Hold your finger up in front of your face, close one eye, then switch. Your finger appears to jump against the background, not because anything moved, but because your two eyes are separated by a few centimeters, and that separation gives you two slightly different viewing angles. Your brain uses that difference to calculate depth. That's parallax, and it's the same fundamental principle Bessel used to measure the distance to the star 61 Cygni, the first time any human being had successfully worked out how far away another star actually was. The difference is scale. Bessel wasn't using two eyes separated by a few centimeters. He was using Earth's entire orbit around the Sun as his baseline. Here's how it works. Pick a nearby star and observe it carefully against the distant background of stars behind it. Then wait 6 months when Earth has traveled to the opposite side of its orbit, roughly 300 million kilometers from where you started. Observe the same star again. If the star is close enough, it will appear to have shifted very slightly against that distant background. Measure the angle of that shift, apply some basic trigonometry, and you get the distance. The geometry is straightforward. The measurement is not. Here's where things get uncomfortable for anyone hoping this was easy. The angular shifts involved are almost insultingly small. For a star, even a few light years away, you're measuring an angle that barely exists. For Proxima Centauri, that angle, called the parallax angle, is 0.77 arcseconds. An arcsecond is 1/3600th of a single degree. To give you a sense of what that looks like, take a single human hair and hold it at arm's length. No, further. Hold it 10 meters away, about 33 feet. The width of that hair at that distance is roughly 1 arcsecond. That is the angular shift you're trying to detect in a star that's over 25 trillion miles away. Bessel didn't have the tools to measure Proxima Centauri specifically, but the method he proved in 1838 was the crack in the door. Every stellar distance measurement for the next century and a half built on that same geometry. The technique has its limits. Parallax works reasonably well out to a few hundred light years, but beyond that, the angular shifts become too small even for precision instruments to catch. Astronomers developed other methods, using the known brightness of certain types of stars as standard candles, for instance, to push the distance ladder further out. But for nearby stars like Proxima Centauri, parallax remains the gold standard, and the precision of the measurements has become genuinely extraordinary. In 2013, the European Space Agency launched the Gaia satellite specifically to map the positions and distances of stars with a precision that ground-based telescopes couldn't touch. Gaia doesn't blink. It isn't disturbed by weather or atmospheric distortion. It rotates slowly and continuously, scanning the sky, measuring stellar positions to within micro-arcseconds, millionths of a single arcsecond. By 2018, Gaia's second data release had pinned the distance to Proxima Centauri at 4.2465 light years. The uncertainty on that measurement is so small it barely registers. We are not guessing. We are not estimating within a margin of millions of miles. We know where Proxima Centauri is with a precision that would have seemed like fantasy to Friedrich Bessel. What makes this remarkable isn't just the number. It's what it means that we got the number without going anywhere. We've never sent anything to Proxima Centauri. No probe has crossed even a fraction of that distance. We worked this out from a single planet, using geometry and patience and eventually a very expensive telescope in Earth's orbit. The entire measurement relies on the fact that Earth moves and that stars shift slightly as it does, and that we can detect that shift with enough precision to calculate a distance across 25 trillion miles. That's a genuinely impressive thing to pull off from your home planet. But there's a particular kind of frustration that comes with precision. The more accurately you know a distance, the less room there is to hope you were wrong. If the measurement were rough, if there were a real chance the distance was half what we thought, then maybe the problem wasn't as severe as it seemed. But it isn't rough. We know the number. We know it to 4 decimal places. And the number is 4.2465 light years, which works out to 25.26 trillion miles. And there is no measurement error hiding a more manageable reality on the other side of that calculation. We know the distance to Proxima Centauri with more accuracy than ancient navigators knew the distance across the Mediterranean, which is remarkable and also does nothing to make the journey any shorter. There's something genuinely strange about what it means to look at a star, and it goes beyond the distance. When you look at Proxima Centauri through a telescope, the light entering your eye left that star 4.24 years ago. Not approximately, not roughly. The photons hitting your retina right now departed their source before they reached you, before tonight, before last year, before several years ago. You are not seeing Proxima Centauri as it is. You are seeing it as it was. That's not a poetic way of putting it. That's the physics of what's actually happening. Here's where this gets uncomfortable. The star you're observing might have changed in that time. Proxima Centauri is a violent flare-prone star. It erupts. In the 4.24 years it took that light to reach you, something significant could have happened to that star, and you would have no way of knowing yet. The information about it simply hasn't arrived. You're watching a broadcast that's running more than 4 years behind. Now extend that logic outward. Sirius, the brightest star in the night sky, is 8.6 light years away. When you look at Sirius, you're seeing it as it was 8.6 years ago. Betelgeuse, the bright red star in Orion's shoulder, sits about 700 light years out. The light reaching your eyes from Betelgeuse left that star roughly around the year 1325. Medieval Europe was in the middle of a plague. That's when those photons departed. Go further. The Andromeda Galaxy is 2.5 million light years away. Every image you've ever seen of it shows Andromeda as it looked 2.5 million years ago, when early humans were still learning to use stone tools and the entire scope of human civilization hadn't even begun to form. The stars in those photographs may not exist anymore. Entire solar systems may have formed and died in the time that light spent crossing the void between that galaxy and your telescope. This is what astronomers mean when they say telescopes are time machines. Not in a metaphorical sense. In a literal, physical sense, looking deeper into space means looking further back in time. The most powerful telescopes we've built can observe galaxies so distant that the light reaching us left them when the universe was only a few 100 million years old. We are watching the early universe right now. It just took the light this long to get here. Pull that back to Proxima Centauri and what it means for communication. Speed of light is not just a travel speed, it's the speed of information. Nothing, no signal, no message, no data of any kind, can cross space faster than light. If you sent a radio transmission toward Proxima Centauri right now, the signal would leave Earth at 300,000 kilometers per second and still take 4.24 years to arrive. There's no shortcut. There's no faster channel. That's as fast as the universe allows anything to move. So the signal arrives 4.24 years from now. Whoever or whatever received it sends a reply immediately. That reply travels back at the same speed. It reaches Earth 4.24 years after that. Total elapsed time, just over 8.5 years for one exchange. One question, one answer. Nearly a decade. Think about what that means in practice. If a spacecraft launched tomorrow and sent a distress signal the moment it arrived at Proxima Centauri, we wouldn't hear it for 4.24 years after transmission. Our response, whatever help we could offer, wouldn't reach them for another 4.24 years after that. By the time a real-time conversation was even theoretically possible, the crew would have been waiting nearly 9 years for us to say anything useful back. That's not a communication delay in the way we normally think about it. It's a fundamental severing of any meaningful connection. Compare that to what we're used to. The Apollo astronauts on the moon had a communication delay of about 1.3 seconds. Mars, at its farthest, has a delay of around 24 minutes. Those are manageable. You can coordinate a mission with a 24-minute delay. You cannot coordinate anything meaningful across 4.24 light years. The crew is, in every practical sense, on their own, operating with information that is years out of date and unable to receive useful guidance in any time frame that matters. If there were people at Proxima Centauri right now and you wanted to have a conversation with them, the absolute minimum time for a single round-trip exchange, one question and one answer, would be 8.5 years. Proxima Centauri, despite being the star we've been talking about for the last several minutes, is not a star you've ever seen in the night sky. And there's a good reason for that. It's invisible. Completely, totally invisible to the naked eye. The night sky you've looked up at your entire life, every star you've ever pointed at, every constellation you've ever traced, none of them include Proxima Centauri. Its apparent magnitude is 11.13. For reference, the human eye can detect objects down to about magnitude 6 under perfect conditions. Proxima is nearly 200 times too faint to register. You would need a reasonably powerful telescope just to confirm it exists. Our nearest stellar neighbor has never once appeared to any human eye without optical assistance, and that invisibility tells you almost everything you need to know about what kind of star this actually is. Proxima Centauri is a red dwarf. That classification might sound exotic, but red dwarfs are actually the most common type of star in the Milky Way. By most estimates, around 70 to 75% of all stars in our galaxy are red dwarfs. Our sun is the unusual one. When you imagine a typical star, the picture in your head, the brilliant, white-hot sphere blazing in the center of a solar system, that's the exception, not the rule. The universe mostly runs on something much smaller, cooler, and dimmer. Here's how small. Proxima Centauri has a mass of about 12.5% of the Sun's mass. Its diameter is roughly 1/7 of the Sun's. To put that in concrete terms, it's only about 50% larger than Jupiter. Not 50% larger than Earth, 50% larger than Jupiter, which is already 11 times wider than Earth. Our Sun could swallow over 1 million Earths. Proxima Centauri could swallow a few thousand at most. If you place them side by side, the Sun would look like a beach ball next to a golf ball. And that golf ball is what we've been calling our nearest stellar neighbor. The surface temperature follows the same pattern. The Sun burns at roughly 5,778 Kelvin, which is why its light looks white-yellow and fills a clear sky with blinding intensity. Proxima Centauri's surface temperature sits at around 3,100 Kelvin. That's barely more than half as hot. At that temperature, the star glows a deep, dull red. Not the vivid orange red of a sunset, but something closer to the color of a heating element on a stove just before it gets truly hot. Dim, smoldering, more ember than fire. Now think about what that means if you're standing on a planet in that system. The star above you would not look anything like the sun. It would be a small, reddish disk in a sky that never quite gets the bright blue wash we're used to. The light hitting the ground would be reddish and low intensity, closer in quality to our twilight than our noon. Colors would look wrong. Shadows would be deep and strange. Everything about the visual experience of that sky would feel alien in a way that's hard to fully imagine from where we're standing. And here's something that makes it even stranger. More than 85% of the energy Proxima Centauri emits comes out as infrared radiation, not visible light. Your eyes wouldn't catch most of what it's actually putting out. Invisible wavelengths specifically, Proxima Centauri is only about 0.0056% as luminous as the Sun. Its total luminosity across all wavelengths is 0.16% of the Sun's. That is not a rounding error. That is a fundamentally different category of object. This is why it's invisible from Earth despite being the closest star. Distance matters, obviously, but even if you moved Proxima Centauri to the same distance as Sirius, the brightest star in our sky, it would still be far too faint to see without a telescope. It's not hidden from us by distance alone. It's hidden from us because it barely puts out enough light to register at any reasonable range. And yet, and this is where things start to get complicated, that very dimness is what makes Proxima Centauri interesting as a place where planets might support life. Because the star is so faint, any planet that wants to be warm enough to have liquid water has to orbit extremely close. We're talking about distances far smaller than Mercury's distance from the Sun. Proxima b, the planet we'll get to shortly, completes a full orbit in 11.2 days. It sits about 7.5 million kilometers from its star. Earth orbits the Sun at 150 million kilometers. That's how close a planet has to get just to be warm enough. At that distance, the star isn't a distant light source. It's directly overhead, enormous relative to its surroundings, filling a chunk of the sky with that dull red glow. And at that distance, the planet is locked into Proxima Centauri's gravitational grip in ways that create their own severe problems. But we'll get to those. The more immediate issue is what happens to something that close to a red dwarf, because red dwarfs have a habit that their calm appearance does not prepare you for. Proxima Centauri looks quiet. It looks dim and cool and almost gentle compared to the raging nuclear furnace of our own sun. But that appearance is deeply misleading. The closeness that makes a planet warm enough for liquid water is the same closeness that puts it directly in the line of fire for everything Proxima Centauri does when it loses its temper. Here's where the story about our nearest stellar neighbor starts to get genuinely grim. We spent the last few minutes establishing what Proxima Centauri actually is, a dim, cool red dwarf, small and ancient, radiating mostly in infrared, invisible to the naked eye despite being the closest star in the universe to our own. And there's something almost comforting about that picture. A quiet little star, modest by any measure, sitting out there in the southern sky with at least one planet tucked in close enough to stay warm. But that comfort doesn't last, because Proxima Centauri has a temper. The scale of it is genuinely difficult to process. Red dwarf stars are the most common type of star in the Milky Way. They're small, they burn slowly. They last for hundreds of billions of years, far longer than our sun ever will. What the textbooks don't always emphasize is that small and quiet are not the same thing. Red dwarfs and Proxima Centauri in particular produce stellar flares, not the modest solar flares our sun occasionally generates, the ones that sometimes disrupt GPS signals and produce beautiful auroras near the poles. We're talking about something in a completely different category. Proxima Centauri erupts, regularly, violently, and with consequences that reshape the question of whether anything could survive on the planets orbiting it. In 2016, the same year astronomers announced the discovery of Proxima b, researchers observed a superflare from Proxima Centauri that increased the star's optical brightness by a factor of 68. Think about what that means. The star suddenly appeared 68 times brighter than normal in visible light alone. That's not a gentle brightening. That's an explosion of radiation pouring out in every direction. And 2016 wasn't even the record. In 2019, astronomers recorded the largest stellar flare ever observed anywhere in the Milky Way. It came from Proxima Centauri. In ultraviolet wavelengths, the star brightened by a factor of 14,000. For a few minutes, this dim, unassuming red dwarf was producing ultraviolet radiation at 14,000 times its normal output. These aren't rare catastrophic events. Similar flares occur roughly 5 times every year. The reason we didn't observe them sooner is that each one lasts only a few minutes. Proxima Centauri wasn't being watched continuously until relatively recently. They were always happening. We just weren't looking. Now consider what that means for Proxima b, sitting about 7.5 million kilometers from its host star. That's close, far closer than Mercury is to our Sun. When Proxima Centauri fires off one of these superflares, the planet is essentially in the front row. The radiation arrives fast and hits hard, and we're not talking about just visible light. The most dangerous components are the ultraviolet radiation and the X-rays, along with a surge of charged particles called a coronal mass ejection, a plasma cloud launched outward at millions of kilometers per hour. Here on Earth, we're protected from exactly this kind of bombardment by our magnetosphere. The planet generates a powerful magnetic field that extends tens of thousands of kilometers into space, deflecting the solar wind and redirecting charged particles toward the poles. Without that magnetic field, Earth's atmosphere would be slowly stripped away, molecule by molecule carried off by the constant pressure of the solar wind. Mars gives us a fairly clear picture of what happens without one. Mars once had a thicker atmosphere. It also once had a stronger magnetic field. When that field collapsed billions of years ago, the solar wind began eroding the atmosphere. Today, Mars has almost no atmosphere and no liquid water on its surface. The solar wind did that. Proxima b faces something considerably worse than what Mars experienced from our Sun. For the magnetic field protection to work on Proxima b, it would need to be extraordinarily strong, strong enough to deflect not just the ordinary stellar wind. That is already more intense than what Earth receives, but also the periodic surges from those superflares. Whether Proxima b has such a field is completely unknown. We can't measure it from here. What we do know is that the level of radiation bombardment it endures would be devastating to any unshielded surface. The UV and X-ray radiation alone during a major flare event would be enough to break apart complex organic molecules on the surface. Over billions of years of repeated bombardment, any atmosphere the planet once had would likely have been stripped or chemically altered beyond recognition. Any liquid water on the surface would either evaporate into the upper atmosphere and get dissociated by radiation, or freeze. The terminator line, the ring between the permanent day side and permanent night side if the planet is tidally locked. That it probably is, might once have been a plausible habitat. After a few billion years of super flares, the picture is considerably less inviting. This is the part that makes the Proxima Centauri system so frustrating to think about. Red dwarf stars are the most common stars in the galaxy. Their habitable zones are close in. That means rocky planets form there frequently and stay warm without needing to be very far out. The universe is full of red dwarfs. Statistically, the universe is full of planets orbiting inside their habitable zones. For a while, this looked like good news for the search for life elsewhere. More habitable zone planets means more chances. But the flare problem doesn't go away just because we want the numbers to work out. The same physics that makes red dwarfs long-lived and gentle in their ordinary output makes them prone to these violent magnetic outbursts. The type of star most likely to host a planet at the right temperature for liquid water turns out to be the same type of star most likely to blast that planet with enough radiation to kill everything on its surface. In 2016, astronomers announced something that immediately made the already interesting Alpha Centauri system into the most discussed star system in the world. A planet, not a gas giant, not some oversized distant blob of hydrogen. A rocky, roughly Earth-sized world orbiting Proxima Centauri, sitting in what astronomers call the habitable zone, the distance range where liquid water could theoretically exist on a surface. After decades of staring at that dim red star, this was the discovery that shifted everything. The nearest star wasn't just interesting because of its proximity. It might be interesting because something could be living there. The planet is called Proxima Centauri b, and the way it was found is worth understanding because it tells you something important about the limits of what we actually know. Proxima b was not detected by photographing it. It was detected by watching the star wobble. This is called the radial velocity method, and here's how it works. When a planet orbits a star, gravity isn't a one-way street. The planet pulls on the star just as the star pulls on the planet. The star doesn't sit perfectly still. It traces a tiny circular or elliptical path in response to that gravitational tug. From Earth, we can't see that movement spatially. The distances are too enormous, but we can detect it by watching the star's light shift. When the star moves slightly toward us, its light gets compressed into slightly shorter wavelengths. It shifts toward the blue end of the spectrum. When it moves slightly away, the light stretches into longer wavelengths and shifts toward red. This is the Doppler effect, the same phenomenon that makes an ambulance siren rise in pitch as it approaches and fall as it drives away. By tracking those tiny shifts in Proxima Centauri's light, astronomers could extract the signature of a planet's gravitational influence. They measured a wobble of about 1.4 meters per second. That's roughly walking speed, and from that almost imperceptibly small signal, they concluded an entire planet was there. Proxima b completes a full orbit every 11.2 days, which tells you immediately how close it is to its star. For comparison, Mercury takes 88 days to orbit the Sun, and Mercury is already considered extremely close. Proxima b is orbiting at about 7.5 million kilometers from Proxima Centauri. That sounds far, but our Earth is 150 million kilometers from the Sun. Proxima b is 20 times closer to its star than we are to ours. The reason this doesn't automatically cook the planet is that Proxima Centauri is so much dimmer than our Sun. The energy output is a tiny fraction of what our Sun produces, which means a planet has to be very close to receive even a survivable amount of warmth. Proxima b lands more or less in that zone. The mass estimate is the part that genuinely gets attention. Based on the wobble amplitude, Proxima b has at least 1.07 times the mass of Earth. At least because the radial velocity method only captures the component of the star's motion toward and away from us. which means we're probably underestimating the planet's true mass depending on the orbital inclination. But in the rough language of planetary science, this is an Earth-mass planet, a rocky world, not a gas giant, something potentially with a surface. Here's where things get more complicated. Proxima b is not the only planet in this system. In 2025, the European Southern Observatory confirmed a second planet using a spectrograph called NIRPS, the Near Infrared Planet Searcher. This planet is designated Proxima d, and it is remarkably small, about 1/4 the mass of Earth, making it one of the lightest exoplanets ever detected anywhere. It orbits even closer to the star than Proxima b, completing a full orbit in just 5 days. Whether it falls in the habitable zone is a much harder argument to make, but the fact that we could detect something that small orbiting a dim star over 4 light-years away is its own kind of extraordinary. There's also Proxima c, a candidate that would orbit much farther out if it exists at all. It would be something like a gas dwarf, significantly more massive than Earth on a much wider orbit. But the evidence for Proxima c is disputed, and calling it a confirmed planet at this stage would be overstating what the data actually supports. It's worth knowing it might be there. It's not worth treating it as established. What's important to sit with is that we have never seen any of these planets. Not one of them has been directly imaged. No photograph exists. No telescope has captured a pixel of light reflected off Proxima b's surface. Everything we know about these worlds, their masses, their orbits, their distances from the star, comes from reading the gravitational signatures they leave on their host star. We are inferring their existence from the tremors they produce in something we can observe from 25 trillion miles away. It is an astonishing act of inference. It is also a profound limitation on what we actually know. We don't know what Proxima b looks like. We don't know if it has an atmosphere. We don't know if there's water on its surface, under its surface, or nowhere at all. We don't know its color, its terrain, or whether it has any distinguishing features beyond a mass estimate and an orbital period. In a meaningful sense, these are worlds we know exist and have never seen, and won't until we send something there. 3 worlds orbiting our nearest neighbor, none of them photographed, all of them inferred from the subtle gravitational tremors they leave on their host star, and at least one of them sitting squarely in what might be the habitable zone. Proxima b sits in what astronomers call the habitable zone, the range of distances from a star where temperatures could, in principle, allow liquid water to exist on a rocky surface, but that designation comes with more asterisks than the official announcement made clear. The habitable zone is not a guarantee of anything. It's a calculation based on distance and stellar output. It says, at this orbital distance, liquid water is thermodynamically possible. It says nothing about whether an atmosphere exists to maintain pressure, nothing about radiation, nothing about magnetic fields or geological activity. The habitable zone is a starting point, not a conclusion. And in the case of Proxima b, almost every factor we can estimate works against the optimistic reading. Start with the orbit. Proxima b completes 1 full trip around its star every 11.2 days. That's the length of its year. Our moon takes 27 days to orbit Earth. It's tidally locked. One face always toward us, one face always pointed away. At 11.2 days, Proxima b is so close to its star, has been for so long that the same tidal forces have almost certainly frozen it in the same configuration. One hemisphere locked in permanent daylight, the other in permanent darkness. The boundary between them, called the terminator line, runs pole to pole like a seam on a baseball, and it never moves. Think about what that means for a surface. The day side receives constant stellar radiation from a star just 7.5 million kilometers away. Our own sun sits 150 million kilometers from Earth. Even though Proxima Centauri is far dimmer, that orbital proximity drives intense surface heating on the day side. Temperatures could reach somewhere above 80 degrees Celsius, potentially much higher depending on atmospheric conditions. The night side, permanently shielded from its star, radiates heat into space indefinitely, probably dropping well below negative 100 degrees Celsius. A planet with one hemisphere baking and one hemisphere frozen solid is not obviously a planet where life thrives. The region that gets the most attention is the terminator, that narrow strip between light and darkness where temperatures might be moderate, not scorched, not frozen. In principle, liquid water could exist there, but that zone would also be the site of permanent violent atmospheric circulation. Hot air rising on the day side, flowing toward the night side at altitude, cooling and sinking, returning along the surface. That cycle doesn't start and stop with seasons. It runs constantly at high intensity, driven by a temperature differential that never equalizes. We're talking about permanent planetary scale windstorms. Whether any surface water in that zone stays liquid, accumulates, or gets stripped away in the process is genuinely unknown. And this is where the atmosphere question becomes the central one. Without an atmosphere, none of this matters. There's no liquid water anywhere in the surface. This was because there's not enough pressure to keep it liquid. Water either boils off immediately or freezes solid. Mars is the local example we reach for here. Mars once had an atmosphere, probably a reasonably thick one. What stripped it? The solar wind, a constant stream of charged particles flowing outward from our sun. Mars lost its magnetic field early in its history. Without that shield, the solar wind eroded its atmosphere over hundreds of millions of years. Behind the thin wisp of mostly carbon dioxide we observe today. The result is a cold, dry, radiation-soaked surface that is essentially hostile to life as we understand it. Proxima Centauri generates a stellar wind too. There's good reason to think it's more intense than our sun's, particularly during the flares described in the previous section. If Proxima b lacks a strong magnetic field, and we have no way to measure that from here, its atmosphere is exposed to that same erosive process. Over timescales measured in billions of years, the planet is estimated to be roughly the same age as the rest of the Proxima Centauri system. That means it's had billions of years of exposure to a hyperactive, flaring red dwarf. If the atmosphere was going to be stripped, there's been plenty of time. Here's where the science is honest about its limits. We detected Proxima b by watching its star wobble. The gravitational tug of the planet causes Proxima Centauri to shift slightly toward and away from us at a measurable rate. From that wobble, we can extract the orbital period and a minimum mass estimate. That's essentially all we have. We have not measured the planet's radius, so we don't know its density, and we can't confirm whether it's rocky. We haven't detected its atmosphere, so we don't know whether it has one, what it's composed of, or how thick it might be. We have no surface temperature data. We have no direct image. The planet is inferred, not observed, and everything beyond the basic orbital parameters is extrapolation based on models. That said, models do point toward one genuinely interesting possibility: subsurface liquid water. If Proxima b has a rocky interior generating heat through radioactive decay, if there's water ice present, the ice at depth could be melted by that internal heat regardless of what's happening on the surface. Europa, one of Jupiter's moons, operates on exactly this principle. A global ocean kept liquid not by sunlight but by tidal heating deep in the rock. A subsurface ocean on Proxima b would be shielded from radiation, shielded from stellar wind, and potentially chemically active. Whether that's enough for biology is a separate question. But it's not a question you can dismiss simply by pointing to the hostile surface conditions above. So here's the honest accounting. Proxima b might have an atmosphere, or it might not. It might have liquid water somewhere on or below its surface, or it might be dry. It might have moderate temperatures in a thin terminator band, or those temperatures might be unstable. It might have a protective magnetic field, or it might have been stripped of its atmosphere billions of years ago. We don't know, and with current instruments at current distances, we can't determine any of these things definitively. Every question about Proxima b's habitability eventually loops back to the same answer. We need to get closer. That is precisely the thing we cannot yet do. To really feel the problem in its full weight, it helps to go through our actual spacecraft one by one and work out how long each of them would take to reach Proxima Centauri. Let's start with Voyager 1. Launched in 1977, it's the most distant human-made object in existence. It has crossed the heliopause, the boundary where the sun's influence gives way to interstellar space, and it is genuinely right now traveling through the space between stars. Its current speed is about 17.3 kilometers per second. That sounds fast. It is fast by any standard a human being would encounter in daily life. At that speed, Voyager 1 would take over 73,000 years to reach Proxima Centauri. Not 73,000 days, not 73,000 months, 73,000 years. Agriculture was invented roughly 12,000 years ago. We are talking about a journey 6 times longer than the entire history of farming. New Horizons is another benchmark worth considering. It flew past Pluto in 2015 and sent back those extraordinary close-up photographs that shocked even the scientists who built it. At the time of its Pluto flyby, it was moving at around 58,000 kilometers per hour, making it among the fastest spacecraft ever launched from Earth. Pointed at Proxima Centauri, and the math works out to approximately 80,000 years. That's longer than modern Homo sapiens have existed as a distinct species. Here's where things get uncomfortable in a very specific way. The Parker Solar Probe is humanity's speed record holder at its closest approach to the Sun. It doesn't maintain that speed constantly. It dips toward the Sun, gets flung forward by gravity, and hits peak velocities of around 692,000 kilometers per hour. Nothing we've ever built moves faster. At that peak speed, directed straight toward Proxima Centauri, the travel time comes down to roughly 7,200 years. That is the best number we have. Our fastest spacecraft, our finest engineering, 7,200 years. Now sit with that figure for a moment. The Great Pyramids at Giza were constructed about 4,500 years ago. Written language was developed around 5,000 years ago. The Parker Solar Probe, at its absolute maximum velocity, would still need to travel for longer than the full span of recorded human history before it reached our nearest stellar neighbor. Every empire that has ever risen and fallen, every war, every invention, every document we've ever written, all of that fits inside a window that is shorter than the travel time of our fastest spacecraft to the closest star. And that 7,200-year estimate is actually generous. The Parker Solar Probe doesn't sustain that speed. It achieves it briefly during solar flybys because it's falling toward a massive gravitational body. Out in the open void of interstellar space, there's no sun to slingshot around. The probe would slow dramatically. The real-world number is considerably worse. What about Helios 2? It's a solar probe from the 1970s that still holds the record for the closest deliberate approach to the sun ever made by a spacecraft. At its closest point, it reached about 240,000 kilometers per hour, not as fast as the Parker probe's peak, but a speed it sustained for longer during that approach. If you could somehow hold that speed constant all the way to Proxima Centauri, the journey would take around 19,000 years. Better than Voyager. Still 19,000 years. The pattern here is impossible to talk your way around. Every spacecraft we've ever built, every speed record we've ever broken, produces a travel time measured in thousands of years. The worst estimates run past 80,000 years. The best estimate sits at 7,200. There is no version of this calculation that produces a number a human being could meaningfully wait out. Most people, when they first hear these figures, assume the solution is straightforward. Just build something faster. And that intuition isn't wrong exactly, but it dramatically underestimates how much faster. We don't need an engine that's 10% better than the Parker Solar Probe. We don't need one that's twice as good or 10 times as good. To reach Proxima Centauri before a human lifetime elapsed, you'd require velocities of roughly 10% the speed of light. That's about 107 million kilometers per hour. The Parker Solar Probe, at its fastest, reaches about 692,000 kilometers per hour. Closing that gap requires going roughly 150 times faster than the quickest thing humanity has ever launched. That's not an incremental engineering problem. That's not a matter of better materials or smarter design. The spacecraft we have today aren't on a development curve that leads naturally to interstellar capability. They're on a curve that leads to marginally faster solar probes and more efficient orbital maneuvering, which is genuinely valuable. But it does not close a 150-fold speed gap on any near-term timeline. These aren't numbers that get better if we wait a few years for an upgraded engine. We're talking about a gap between what we have and what we need that spans thousands of years of travel time. The Parker Solar Probe does better, reaching peak speeds around 600 to 92,000 kilometers per hour during its close solar passes. That's a genuine leap, but we've already seen what that buys, about 7,200 years to Proxima Centauri. Still longer than recorded human history. Here's the thing most people don't realize about that speed. The Parker Solar Probe doesn't sustain it. It achieves that speed through gravitational acceleration during its inbound plunge toward the sun, which allows it to slingshot itself faster. In deep interstellar space, there's nothing to fall toward, no massive body to borrow energy from. You'd need constant propulsion to maintain speed, and constant propulsion means fuel, and fuel is mass, and accelerating mass requires more fuel. The rocket equation bites you again. So if chemical rockets are off the table, what's actually on it? The honest answer is a ladder of increasingly exotic propulsion concepts, each one more powerful than the last, each one bringing its own completely different set of problems. None of them exist as flight-ready hardware. Some of them barely exist on paper, but they represent the serious thinking that physicists and engineers have done about what it would actually take to close this gap. And walking through them in order tells you something important about just how steep the climb is. The first rung is nuclear thermal propulsion. The basic idea is straightforward enough. Instead of burning chemical propellants to produce heat, you run hydrogen through a nuclear fission reactor, and the reactor heats it to temperatures no chemical reaction could reach. Then you expel it out the back as thrust. The efficiency roughly doubles compared to the best chemical rockets. That sounds promising until you do the math and realize that doubling the efficiency of something that falls about 10,000 times short of what you need doesn't actually move the needle on interstellar travel. Nuclear thermal propulsion is genuinely useful for missions within the solar system, cutting travel time to Mars significantly. For instance, but for reaching Proxima Centauri, it's still measured in thousands of years. NASA and DARPA are currently developing a test vehicle called Draco, the demonstration rocket for agile cislunar operations. That would test a nuclear thermal engine between Earth and the Moon. That's real progress. It's just not interstellar progress. The next rung is where things get significantly more extreme. Project Orion, studied seriously in the 1950s and early 1960s, proposed something that sounds almost satirical at first. Detonate nuclear bombs out the back of your spacecraft. Use a reinforced plate to cushion the explosive force. Ride the explosion forward, over and over again, thousands of times. Computer simulations suggested this could actually work, that a large enough Orion vehicle could reach somewhere between 3% and 5% of light speed. At 3% light speed, you're looking at roughly 140 years to Proxima Centauri. That's multi-generational, but it's in a different category entirely from 7,000 years. The problems, though, are severe. You need thousands of nuclear weapons. The radiation exposure to the crew would be intense, even with shielding. The engineering of a shock plate that can absorb repeated nuclear detonations without destroying itself is deeply uncertain. And perhaps most definitively, the 1963 Partial Test Ban Treaty. That prohibited nuclear detonations in the atmosphere and in space, effectively ended any realistic path toward testing or launching such a vehicle. Project Orion is one of those ideas that was technically serious and politically impossible. That in practice means it's the same as impossible. Fusion drives are the next step up, and they're where the numbers finally start looking genuinely interesting. The concept uses deuterium and helium-3 pellets detonated inside a magnetic containment chamber to produce plasma that's directed out the back of the spacecraft as thrust. Theoretical calculations suggest a fusion rocket could reach about 12% of light speed. At that speed, Proxima Centauri is about 36 years away. That's a human lifetime. That's actually a mission someone could survive and complete. Here's where things get uncomfortable, though. Helium-3 is essentially non-existent on Earth. The Moon's surface has some deposited over billions of years by the solar wind, but extracting it in the quantities required would demand a mining operation on the lunar surface that dwarfs anything we've built. The outer planets, particularly Jupiter and Uranus, have much larger reserves, but reaching them to mine them requires the kind of propulsion infrastructure we're supposedly still developing, and that's the secondary problem. The primary problem is that we haven't achieved controlled nuclear fusion at all. Researchers have been working on it for over 70 years. We've gotten closer. The National Ignition Facility achieved ignition in 2022, producing more energy from a fusion reaction than the lasers put in. That's a real milestone, but a single ignition event in a laboratory is an enormous distance from a compact, reliable fusion reactor running continuously for decades in the back of a spacecraft. Optimistic projections put a practical fusion power plant on Earth perhaps 20 to 30 years away. A fusion rocket is further than that. Then there's antimatter. This is the top of the ladder, theoretically speaking. This was because antimatter annihilation is the most energy-dense reaction that physics permits. When a particle of matter meets its antimatter counterpart, they don't just burn, they convert completely into energy. Every gram, every atom, 100% converted, in accordance with E equals mc squared. Nothing is wasted. The theoretical efficiency of an antimatter drive makes everything else look primitive. A few kilograms of antimatter, properly directed, could in principle accelerate a spacecraft to a meaningful fraction of light speed. The problem isn't the physics. The problem is the antimatter itself. The total amount of antimatter humanity has ever produced across every particle accelerator on Earth. across every experiment ever run is less than 20 nanograms. That's a number so small, it's almost impossible to visualize. If you took all the antimatter ever made and annihilated it against an equal amount of regular matter, the energy released would be enough to power a small light bulb for a few minutes. Scaling from 20 nanograms to the kilograms you'd need for a spacecraft drive is not an engineering challenge. It's a production challenge that, at current rates, would take longer than the current age of the universe to solve. And that assumes you can store it. Antimatter cannot touch any ordinary matter without annihilating instantly. That means it has to be held in magnetic conte, meant fields indefinitely with zero failures for years or decades. A single containment failure doesn't just end the mission, it releases energy equivalent to a multi-megaton nuclear weapon inside the spacecraft. This is the pattern that emerges when you go through these systems one by one. Each one is more powerful than the last. Each one gets you closer to the speed you actually need. And each one has a central problem that isn't a matter of engineering refinement. It's a matter of capability gaps that could themselves take decades or centuries to close. At every rung of the theoretical ladder, from nuclear thermal to fusion to antimatter, you climb one engineering problem only to find three more waiting at the top. The most serious near-term proposal for actually getting something to another star doesn't involve rockets at all. After everything we've just walked through, the nuclear pulse detonations, the fusion drives, the antimatter containment nightmares, the most credible near-term concept strips all of that away and replaces it with something almost elegant: light itself. Photons carry momentum. When they strike a reflective surface and bounce back, they transfer a tiny push to whatever they hit. This isn't theoretical. The Japanese spacecraft Icaros demonstrated it in 2010. Unfurling a reflective sail in space and measuring the genuine, if small, acceleration from sunlight alone. The physics works. The question is whether you can scale it into something useful. Here's what useful would look like. Build a laser array, either on the ground or in orbit, capable of producing around 100 gigawatts of focused power. That's the output of roughly 100 large power plants, all aimed at a single point. Then build your spacecraft, not a rocket, not a crewed vessel, but something about the size of a postage stamp. A gram or two of electronics, cameras, sensors, a basic transmitter, attached to a sail a few meters across, made from material thin enough that the whole thing barely registers on a scale. Fire the laser at that sail for a few minutes. The acceleration is violent and almost incomprehensible. At the end of those few minutes, the spacecraft is moving at roughly 20% the speed of light, about 60,000 kilometers per second. That is what Breakthrough Starshot, announced in 2016 and backed by significant funding, proposes to do. At 20% light speed, Proxima Centauri is a 20-year journey. Not 7,000 years, not 80,000 years, 20 years. For the first time in this entire conversation, we're talking about a number that fits inside a human life. But before we get too excited, we need to talk about what actually has to go right here, because the list is long. The first problem is the laser itself. A 100 gigawatt array doesn't exist. Nothing close to it exists. The entire electrical generating capacity of the United Kingdom is roughly 75 gigawatts, and we're talking about focusing 100 gigawatts of laser energy, not general electricity, laser energy, onto a target a few meters across. The engineering required to build that array, power it, cool it, and point it with sufficient accuracy is a challenge that dwarfs anything currently on any country's roadmap. This is decades of development at minimum and likely cost in the hundreds of billions. The second problem is the precision. Your sail is a few meters wide. Within the first few seconds of acceleration, it's already moving away from you at thousands of kilometers per second. The beam has to track it continuously, keep it centered, and do so without drifting off axis. Because if the beam catches the edge of the sail at an angle, the craft spins out of control and the mission ends. The tolerances required are extraordinary. Any vibration in the laser array, any atmospheric distortion in the beam path, any deviation in the sail's orientation introduces error that compounds faster than any correction system can respond. Third problem, the spacecraft itself. At 1 gram, there is almost nothing there. You can fit cameras, maybe a few basic sensors, a transmitter, and that transmitter is where things get difficult. To send a meaningful signal across 4.24 light-years, you need power, real power. A gram-scale craft has almost none to spare. You might get a few images back, a handful of data points. Whatever it manages to transmit leaves Proxima Centauri and spends 4 more years traveling back to Earth. So the total wait from launch to data receipt is somewhere around 24 years. Your scientists who design the mission will be in their late careers or retired by the time anything arrives. Fourth, and this one tends to stop people cold, there is no way to slow down. The same laser that accelerated the craft is left behind on Earth. Nothing at the destination can decelerate it. At 20% light speed, the craft screams through the Proxima Centauri system in a matter of hours, maybe less. It has that window to collect data, fire its transmitter, and capture whatever it can. And then it's gone. Permanently. It doesn't enter orbit. It doesn't stop to look around. It doesn't come back. It exits the system at 20% light speed and continues into the void forever, no different in its fate from a bullet fired into the dark. What we'd get back, best case, is extraordinary compared to what we have now. Direct images of Proxima b, atmospheric data from a close pass, magnetic field readings, temperature measurements, confirmation or denial of conditions that might support life. For the first time, we wouldn't be inferring from wobbles and light curves. We'd have actual photographs of an actual world orbiting our nearest star. That would be remarkable. Nobody is dismissing what Breakthrough Starshot is attempting to achieve, but it's worth being precise about what it is and what it isn't. It isn't a mission to Proxima Centauri. It's a flyby at 1/5 of light speed by a chip with a camera. It cannot stop. It cannot return. It cannot be redirected if something interesting appears off to one side. Any data it sends back is 4 years in transit before it arrives. And even this, the most concrete, most funded, most technically grounded proposal on the table, requires technology that doesn't fully exist yet, and a laser array no civilization has ever attempted to build. Every rung of the ladder we've climbed in this conversation has handed us the same lesson. The closer something looks to working, the more the remaining problems come into focus. Starshot is no different. Our most realistic near-term option for interstellar travel is a gram-scale chip that would spend 20 years crossing 4 light-years and then have a few hours to look around before sailing off into permanent exile in the void. Let's set aside for a moment the question of how we'd build the engine and think about what the journey itself would actually be like for the people on it. We've been through the numbers on propulsion, chemical rockets, nuclear pulse, fusion, laser sails. But the human dimension of this problem is different from the engineering dimension, and in some ways, it's harder to process. So let's assume, generously, that someone has solved the propulsion problem. Let's say we've developed a drive capable of pushing a spacecraft to 10% of the speed of light. That's approximately 30,000 kilometers per second. That's 40 times faster than anything we've ever built. And at that speed, the journey to Proxima Centauri takes about 42 years. One way. Think about what 42 years actually means in a human life. If you're 30 years old when you board the spacecraft, you're 72 when you arrive. You will have spent your entire adult life, every decade of your working years, your middle age, the years when most people raise children and build careers and watch the world change, inside a metal structure moving through a void so complete that the nearest star behind you would be our own sun, shrinking to a bright point, and then to something you'd need a telescope to find. Here's where it starts to get uncomfortable. You're not just giving up years, you're giving up the planet. On launch day, the people you love are on the ground. Parents, friends, partners. Whatever world you grew up in, the spacecraft lifts and you watch the cameras. Earth gets smaller. It becomes the thing Carl Sagan described, a pale blue dot against black. And then it becomes a bright star. And then, weeks later, it's gone, indistinguishable from everything else in the sky behind you. The people down there are going to keep aging. They're going to have experiences and lose people and move through the rest of their lives, and none of it will reach you in anything close to real time. A message from Earth takes months to reach you in the early years, and years later on. You're not just far away. You are, in every practical sense, gone. The spacecraft itself would have to be substantial. You're not sending people across the solar system for a few months. You're sustaining a small civilization for 4 decades. The vessel would need living quarters designed not just for sleeping, but for actually living in private space. Because psychological studies of isolated environments, Antarctic stations, submarine crews, have shown that the absence of personal space accelerates conflict in ways that are predictable and serious. You'd need workspaces, laboratories, medical facilities capable of handling anything from a broken arm to major surgery to cancer treatment. You'd need exercise infrastructure because without gravity or without rotation to simulate it, the human body deteriorates in ways that would leave the crew too physically compromised to function on arrival. You'd need recreational space because the alternative is a crew that loses the psychological coherence needed to operate as a team by year 15. How many people? This is a real engineering and social calculation. Too few, and you have a problem every time someone dies or becomes incapacitated. You might lose the only surgeon, the only nuclear engineer, the only person who knows how to repair a critical system. Studies of minimum viable populations suggest you need somewhere between 150 and several hundred people to maintain genetic diversity alone, though smaller crews have been proposed for initial missions. Too many people, and the mass becomes enormous, and the propulsion requirements scale with it in ways that become physically prohibitive. There's no clean answer here. Every option involves accepting serious risk. Now consider the children. People will be born on this ship. If the mission carries families or if relationships form during transit, which is essentially inevitable over 4 decades, children will grow up having never stood on a planet. They'll never have seen an open sky. They'll never have felt rain or wind that wasn't mechanically produced. Their entire frame of reference for what the universe looks like will be corridors, viewports, and the same faces they've known since birth. That's not a hypothetical edge case. It's a demographic reality of a 42-year voyage with any crew large enough to be viable. And here's what happens culturally. Earth doesn't stop while you're gone. Languages evolve over 42 years. Political structures change. Technologies emerge. Cultural references accumulate that you have no context for. The music, the news, the shared experiences that bind a civilization together. The crew receives all of it on a years-long delay, and gradually it stops making the kind of sense it made when they left. The mission that launched them may be celebrated for the first decade, commemorated for the second, and filed under history by the time they're halfway there. The people who plan the mission will mostly be dead or retired before the crew arrives. The institutions that funded it may not exist in the same form. Whatever emotional connection Earth had to the voyage will have competed for attention with decades of subsequent crises and discoveries. The crew, meanwhile, is building something that functions like its own small civilization. Norms develop, hierarchies shift. The culture of the ship in year 30 is not the culture of the ship in year 5. People who were strangers on launch day have become, by mid-journey, the entire known world for each other. They're the only people any of them will ever know again, in any immediate sense. That kind of intensity can produce extraordinary cohesion. It can also produce the kinds of conflict that isolated communities have always produced. And unlike any isolated community in history, there's no option to leave. There's a specific moment that seems worth focusing on. Not the launch, which is full of adrenaline and ceremony and the forward momentum of departure. Not the arrival, which at least offers resolution. The middle. Year 20. You're past the halfway mark by 2 years. The sun is far enough behind you that the solar system is a memory. Proxima Centauri is far enough ahead that its disk is still barely distinguishable from a point of light. The people you knew on Earth are 20 years older, living in a world that's moved on in ways you can only partially track through delayed transmissions. You've spent 2 decades in this structure, and the thought that follows is not abstract. You're 20 years in, surrounded by people you've known for 2 decades, and the thought you can't escape is that you have 22 years left before you arrive at something that might be completely inhospitable, and there is no going back. Power runs underneath all of it. The lights, the water recyclers, the garden, the air processing systems, the medical equipment, the computers, the communications array, the artificial gravity rotation drive. All of it needs continuous power for 42 years. The only realistic option at that scale and duration is nuclear fission. Reactors running without interruption for 4 decades. And reactors produce heat, enormous quantities of it, that has to go somewhere. In space, the void won't naturally dissipate it. You radiate it, large panels extending from the hull, dissipating thermal energy into the void. Those panels add mass. They're also vulnerable exposed surface area on a spacecraft that will encounter the hazards of deep space for half a century. Space, at the speeds we're talking about, stops being empty. We tend to picture interstellar space as a void, dark, quiet, essentially nothing between here and there. And in the technical sense, that's accurate. The density of matter between stars is extraordinarily low. But density isn't the same as danger, and at 10% light speed, the math changes in ways that should make any mission planner extremely uncomfortable. What looks like nothing is actually a field of projectiles. The problem isn't the vacuum. The problem is everything that's floating in it. Start with the smallest threat. A grain of sand, roughly a milligram in mass, is the kind of particle spacecraft already encounter in orbit around Earth. At normal spacecraft speeds, a few kilometers per second, it's a minor concern. It can scratch a solar panel or pit a camera lens. At 10% light speed, that same grain of sand is moving at about 30,000 kilometers per second. Kinetic energy scales with the square of velocity. So when you increase speed by a factor of roughly 10,000 compared to something like the International Space Station, the energy doesn't go up by 10,000. It goes up by 100 million. That milligram of sand now carries the energy of several kilograms of TNT. It hits your hull and detonates like a shaped charge. A pebble, a few grams, hits with the force of a small nuclear weapon. This is not a remote or theoretical concern. Interstellar space contains dust. It contains gas. It contains particles so small they've never been cataloged individually and never will be. At the speeds required to reach Proxima Centauri in any reasonable time frame, every one of those particles is a bullet. Every centimeter of travel presents exposure, and you're covering 40 trillion kilometers of this. The engineering response is shielding. Put something in front of the spacecraft, a thick disk of material. Some designs propose graphite or similar ablative composites mounted far ahead of the main body on a long boom. As particles hit the shield, they vaporize on impact, and the resulting plasma expands and disperses before it can damage the craft behind it. It also adds enormous mass. More mass requires more thrust. More thrust requires more fuel. More fuel adds more mass. And shielding can only do so much. Magnetic fields can deflect charged particles, protons, electrons, ionized atoms, which is actually useful for another threat. But neutral particles, uncharged dust and atoms, pass right through magnetic fields entirely unaffected. The shield disk is your primary answer to those, and it has to work for 42 years, absorbing impacts continuously. You'd expect it to erode. How fast it erodes depends on the particle density of the specific path, which is poorly mapped over interstellar distances. Navigation compounds the problem in a different way. At 10% light speed, you're crossing about 30,000 kilometers every second. If your sensors detect a hazard ahead, a denser concentration of dust, a larger object, you have fractions of a second to respond. No human pilot can operate at those timescales. The spacecraft needs autonomous navigation systems capable of calculating and executing course corrections faster than any person could process the input. And those corrections need to be small because at 10% light speed, even a slight lateral burn changes your trajectory significantly over the remaining years of flight. Then there's cosmic radiation. Earth's magnetic field and atmosphere shield us from the constant stream of high-energy particles that pour through the galaxy. Galactic cosmic rays produced by supernovae, black hole jets, neutron star collisions, and other violent events. Out in deep interstellar space, those protections are gone. The crew of an interstellar spacecraft would be exposed to this radiation continuously for the entire duration of the journey. The numbers are troubling. Long-duration exposure to galactic cosmic rays is already one of the main health concerns for a mission to Mars, a journey measured in months. A 42-year interstellar crossing isn't months. The cumulative radiation dose would far exceed any accepted safety threshold. Cancer rates among the crew would be significantly elevated. Some of the highest energy particles, called ultra-high energy cosmic rays, are energetic enough to pass through almost any shielding you could practically carry. You can reduce exposure. You cannot eliminate it. The crew accepts a shortened expected lifespan the moment they depart. Heavy hydrogen shielding, water walls, polyethylene panels, can absorb a portion of the particle flux. A magnetic shielding system running continuously on nuclear power could deflect the charged component. Some designs incorporate a storm shelter, a heavily shielded central compartment where the crew retreats during the most intense radiation events. Relativistic speeds also distort the navigation environment in ways that are less immediately dangerous but still operationally significant. At 10% light speed, light ahead of the spacecraft appears blue-shifted, compressed to shorter wavelengths, while light from behind appears red-shifted. Stars shift their apparent positions toward the forward direction of travel. The star charts the crew departed with are no longer accurate in a straightforward way. Navigating by stellar reference requires corrections for these relativistic effects, adding another layer of computational complexity to a mission that's already operating at the edge of what's technically conceivable. And then there's the structural reality of the spacecraft itself. A vessel hundreds of meters long, under continuous thrust from its engines, is under constant tension. The joint between the propulsion section and the crew habitat is under enormous load. Different parts of the ship, exposed to different amounts of waste heat and cold vacuum, expand and contract on different cycles. Over 42 years, that's hundreds of thousands of thermal cycles on every structural connection point. Metal fatigues, seals degrade. Joints that were certified for a 10-year mission have different failure profiles at 40 years. Space is not the empty, patient void we picture when we talk about these journeys. At the speeds we need, it's a gauntlet with no exits. A grain of sand that would bounce off a satellite in Earth orbit would, at 10% light speed, punch through a spacecraft hull with the energy of several kilograms of high explosive, and the journey to Proxima Centauri runs through 25 trillion miles of that. One of the things people underestimate when they think about interstellar travel is how alone the crew would actually be. Not just physically alone, but cut off from the flow of time on Earth in a way that has no analog in any human experience. We tend to think of communication as something that happens instantly. You send a message, someone reads it. The idea that communication has a speed, that it takes time, is something we know intellectually but almost never feel. Radio signals travel at the speed of light. That's fast enough that talking to someone on the other side of the planet introduces no noticeable delay. Talking to astronauts on the International Space Station, a fraction of a second. Talking to a spacecraft near Mars, somewhere between 3 and 20 minutes each way, depending on where the planets are in their orbits. Inconvenient, but manageable. Mission controllers on Earth can still guide decisions, still respond to emergencies, still feel like they're part of the same story. At interstellar distances, that changes completely. On launch day, the delay is still just minutes. In the first weeks and months, a signal from the spacecraft reaches Earth in hours. But the ship is accelerating. It's putting distance between itself and home at a rate that nothing in human history has ever matched. 1 year out, the signal takes roughly a month to arrive. 1 light year out, it takes a year. And this mission is going 4 light years. The math is simple and completely merciless. By the halfway point, 2 light years out, somewhere around year 21 of the journey, a message to Earth takes more than 2 years to arrive. The reply takes another 2 years to come back. That's over 4 years for a single exchange. You ask a question in year 21, and you get an answer in year 25. Whatever crisis prompted the question has long since resolved itself one way or another, entirely without input from Earth. By the time the spacecraft arrives at Proxima Centauri, after 42 years of travel, a round-trip signal takes 8.5 years. Think about what that actually means for a human relationship. You could send a message to someone the day you arrived, someone who was 30 years old when you left. And by the time they received it, they'd be in their late 70s. Their reply, if they were still alive to send one, would reach you when you were well into old age yourself. The conversation you're trying to have has been interrupted by decades before either side finishes a sentence. Here's where things get genuinely disorienting. The crew would be living in a kind of permanent past. Messages from Earth take years to arrive, so all news is old news. A political event the crew hears about has already concluded. A technological breakthrough they're reading about has already been surpassed. People they loved, parents, friends, siblings, are aging forward on a planet the crew can no longer reach. And the word that someone died arrives years after the funeral. You grieve on a delay, you celebrate on a delay. Every emotional event in your life is separated from its cause by years. There's no real precedent for this. Antarctic researchers are isolated, but they can talk to family in real time. Submariners go dark for months, but they surface. Even the Apollo astronauts on the far side of the moon and temporarily out of contact were only silent for about 45 minutes. The crew of an interstellar mission would be out of contact, not silent but truly out of sync, for the rest of their lives. And from Earth's side, maintaining genuine connection to a mission like this would be extraordinarily difficult. The crew can't respond to breaking news. They can't weigh in on decisions that affect the mission in real time. Early in the journey, when signals still arrive in days or weeks, people on Earth might follow the story with real emotional investment. A decade in, when the crew's messages describe a world that no longer exists and the replies to Earth's questions are 2 or 3 years late, the connection starts to feel more archival than human. Interest fades. The news cycle moves on. The mission that once captured global attention becomes something researchers follow and most people vaguely remember. Funding priorities shift. The government that launched the mission may not exist in the same form by arrival. The agency that built the spacecraft may have been restructured or absorbed. The scientists who designed the instruments the crew is operating have retired or died. The crew is, in a very real sense, carrying out orders from a world that no longer exists, on behalf of institutions that may have changed beyond recognition. You're not just separated from Earth by 25 trillion miles. You're separated from it by years, watching messages arrive from a world that has already moved on to the next crisis while you're still reading about the last one. There's a strategic problem lurking inside the timeline of any early interstellar mission that doesn't get discussed as much as the engineering, and it might be the cruelest one of all. It goes like this. Suppose we develop a propulsion system capable of 10% light speed. The journey to Proxima Centauri takes 42 years. You launch. 20 years later, engineers on Earth crack a more advanced drive, something that pushes a spacecraft to 20% light speed. That second mission launches. It takes only 21 years to make the crossing. Do the math, and here's what you get. The second mission, launched 2 decades after yours, arrives first. You are still 12 years from your destination when a faster ship passes you and enters orbit around Proxima b ahead of you. And depending on how much faster the next generation of technology becomes, this isn't just a theoretical edge case. It's a near certainty if you launch too early. Here's where things get genuinely uncomfortable. We're not talking about arriving second in a race. We're talking about the possibility that by the time your ship reaches Proxima Centauri, there's already infrastructure there. A colony. Answers to all the questions that justified your mission in the first place. You spent your entire adult life in a metal cylinder for a destination that someone else already reached. The scenario has a name in the theoretical literature on interstellar travel. It's called the weight calculation, and the core question it poses is deceptively simple. At what point does the benefit of leaving now outweigh the risk of being overtaken by a later mission with better technology? The math isn't hard to set up. What's hard is that the answer keeps changing based on how fast you expect technology to improve, and nobody actually knows that. Think about what this means for the crew psychologically. You've already lost everything to board that ship. Earth is behind you. The people you loved are aging and dying while you're frozen in transit time. You've passed the psychological threshold of no return. And then, 30 years into a 42-year journey, a message arrives. It left Earth 28 years after your mission launched. It takes 2 years to reach you because you're already deep into the crossing. The message is from the space agency. It's informative, professionally worded. A second mission launched 6 years ago. New propulsion technology. They're moving at 18% light speed. Projected arrival 4 years from now. You still have 12 years left. That message is not science fiction. That's a real contingency any mission planner sending the first ship would have to face. There's no communication blackout policy that makes it go away. The crew would know. So what do you do about it? The obvious answer is to wait. Keep developing technology. Don't launch until you're confident nothing in the foreseeable pipeline will overtake you. But this answer has a fatal flaw. If everyone reasons that way, nobody ever leaves. Technology always has a next generation somewhere on the horizon. The wait calculation becomes a permanent deferral, a logical trap where the rational choice is always to wait a little longer, and the actual mission never launches. This is the paradox at the center of the whole problem. If you go too early, your mission gets overtaken. If you wait, you're always waiting. There's no clean resolution to this. No formula that tells you the moment when launching is clearly better than holding off. You can model it, run projections, argue about projected rates of technological progress, and smart people have done exactly that. The honest answer is that the calculation depends on assumptions you can't verify. What you're left with is not a math problem, it's a values problem. It's a question about what the mission is actually for. If the point is to get information about Proxima b as quickly as possible, then waiting for faster technology is almost certainly the right move. If the point is that humans need to begin the act of interstellar travel, the first reaching, the first crossing, then going early has a different kind of value that doesn't disappear even if a faster ship arrives later. The crew that receives that message 30 years in still crossed the distance. They still lived that life. They still got there. Whether they got there first is one way to measure the mission. It's not the only way, but you'd have to be genuinely committed to that framing to hold on to it in year 31, watching the countdown to arrival tick down while somewhere behind you, a ship built with better tools by people who were children when you launched is closing the gap. Deciding to launch is, in part, deciding to accept the possibility that you will be overtaken, that your sacrifice will be made obsolete by people who came after you, and going anyway. Assume for a moment that you solve every problem: the propulsion, the life support, the radiation shielding, the psychological toll, and after 42 years, you actually arrive. The first problem waiting for you at the end of that journey is one that most people don't think about until it's too late to avoid. Getting to 10% light speed required years of continuous acceleration. Physics doesn't care that you've spent 4 decades getting there. Stopping requires exactly the same energy expenditure in reverse. If you burn through half your fuel getting up to speed, you needed to save the other half for deceleration, which means your ship, at launch, had to carry twice the propellant you actually needed for the cruise phase. That's an enormous mass penalty on day 1. Some engineers have proposed an alternative, a magnetic sail, essentially a set of superconducting loops deployed ahead of the ship to create a kind of electromagnetic drag against Proxima Centauri's stellar wind. The stellar wind acts as a brake. It's an elegant idea. The problem is that Proxima Centauri's stellar wind, despite its violent flaring, is actually relatively weak in the steady baseline sense. Deceleration using that method would be slow, very slow. You might spend years bleeding off speed before you're in any position to enter orbit. And if you can't slow down at all, you do a flyby. You scream through the system at 10% light speed, that's roughly 108 million kilometers per hour, and you have somewhere between a few hours and generously a day to observe everything before the entire system recedes behind you forever. Your instruments are running. Your cameras are recording, and then Proxima Centauri is behind you getting smaller, and you are heading into deep space with no way to turn around. That's not exploration. That's a very expensive photograph. So let's say you stop. You've burned your deceleration fuel, you've shed velocity over months or years, and now you're in orbit around Proxima b. What are you actually looking at? Here's where things get uncomfortable because the honest answer is that we don't fully know yet. What we do know is that Proxima b is rocky and roughly Earth-sized, probably slightly more massive. It orbits its star at about 7.5 million kilometers. For comparison, Earth orbits the Sun at about 150 million kilometers, and it completes one orbit every 11.2 days. At that distance, and given how weak Proxima Centauri's output is, the planet sits in what astronomers call the habitable zone. In theory, temperatures could allow liquid water on the surface, but there's something that number doesn't tell you. A planet orbiting that close to its star almost certainly tidally locked. One face pointed permanently at the star, one face locked in permanent darkness. Forever. The day side could be sitting at temperatures above 300 degrees Celsius. The night side could be below -100. Between them, at the terminator, the narrow strip of eternal twilight running around the planet's edge, there might be a region where temperatures are survivable. The atmosphere, if one exists, would be driving hurricane-force winds around that terminator ring as hot air rises on the day side and cold air floods in from the night side. It would be permanent, not a storm, a permanent condition. Whether there's an atmosphere at all is one of the most important unanswered questions in planetary science right now. You'd find out quickly from orbit. You'd run spectroscopy on the light filtering through the planet's limb as it passes in front of the star. If there's an atmosphere, it absorbs specific wavelengths, and the pattern tells you the chemistry. You're looking for oxygen, methane, carbon dioxide, water vapor. Any of those in the right combination would tell you something. Oxygen and methane together in any significant quantity would be extraordinary, because those two gases react with each other chemically. To have both present simultaneously, something would have to be replenishing them continuously. That something could be biology. It's a signal, not a confirmation, but it's the kind of signal that would stop everyone on the ship cold. If the spectrometer comes back blank, no atmosphere, or an atmosphere of bare rock outgassing and nothing else, you're looking at a different kind of result. There's still the subsurface question. Liquid water doesn't require a surface. Under kilometers of rock shielded from the radiation that Proxima Centauri delivers in regular pulses of violence, thermal energy from the planet's interior could maintain liquid water in subsurface oceans. Life on Earth doesn't need sunlight. There are chemosynthetic ecosystems kilometers underground, thriving in total darkness near hydrothermal vents. If Proxima b has that kind of interior warmth, it could be harboring something in the dark below the rock. You wouldn't know from orbit. You'd need to land something, and that's a different mission entirely. What you might also find, even if the surface looks dead, is chemistry in the rock layers that tells a historical story. Proxima Centauri wasn't always this violent. Red dwarfs actually calm down somewhat over time. Younger red dwarfs flare more. It's possible that billions of years ago, Proxima b had a thicker atmosphere, liquid surface water, and conditions more favorable to the chemistry that precedes life. Organic compounds preserved in ancient geological strata, carbon-rich molecules in rock laid down when the planet was younger, would be a finding with enormous implications. Not life, but the ingredients. The evidence that the process started and then got interrupted. Or you find none of that. The surface is bare, the spectrometer shows nothing interesting. The rock record is stripped and simple. The magnetic field, if the planet has one, is too weak to have protected anything. 4 billion years of flare radiation has done exactly what the physics said it would do, and the planet has nothing to tell you. That's the scenario that doesn't get talked about enough. Not a hostile world that fights back, not an alien biosphere that raises more questions than it answers, just silence, rock and vacuum and the faint red light of a star that was never quite enough. After 4 decades in a metal tube, having given up everything you ever knew, the worst possible outcome isn't a hostile world. It's a silent, airless rock with nothing to say. Here's the question that sits underneath everything else. Given everything we've just walked through, the distances, the travel times, the dangers, the psychological toll, the radical uncertainty of what you'd find, why would anyone actually want to go? It's not a rhetorical question, it's actually one of the more serious questions in the entire conversation. This was because the case for going and the case against going are both legitimate. Pretending otherwise doesn't serve anyone. Let's start with the reasons to go, because there are several, and they're not trivial. The first is the one most people reach for immediately: curiosity. We have spent decades building instruments sensitive enough to detect the gravitational wobble of a planet 4 light years away. What we've found is that there are worlds there. At least one of them sits in the region where liquid water could exist on the surface. We don't know if it has an atmosphere. We don't know if it has oceans. We don't know if anything has ever lived there. And here's the uncomfortable truth about that last question. We cannot answer it from here. No telescope we can build on Earth, no probe we can send at current speeds, no model we can run on any computer will definitively tell us whether life exists or has ever existed on Proxima b. The only way to answer that question is to go. And that question, whether life arose somewhere else in the universe, is arguably the most important scientific question we've ever asked. The second reason is survival. This one is harder to argue with the longer you think about it. Earth is not a permanent address. The Sun is about halfway through its main sequence lifetime. In roughly 5 billion years, it will expand into a red giant and sterilize everything within the inner solar system. 5 billion years sounds like a long time, and it is. But the broader point is that betting everything on a single planet is a strategy with a known failure mode. Asteroids, pandemics, volcanic winters, climate shifts. These are shorter-term versions of the same problem. Becoming a species that can inhabit more than one star system is the only form of long-term insurance that actually works. Every other solution is a delay. Interstellar travel is the only permanent answer to the problem of planetary fragility. Proxima Centauri is the first step on that path. The third reason is harder to quantify, but probably the most honest. Humans are historically at their most focused when the problem in front of them seems impossible. The engineering required to send people to another star would pull on every field of science simultaneously: materials science, biology, physics, medicine, psychology, computer science, agriculture. The problems that get solved in service of an interstellar mission would almost certainly produce technology that improves life on Earth in ways nobody predicted. That's not speculation. It's the pattern every major exploration effort has followed. The question isn't whether the challenge is worth attempting. The question is whether we're willing to attempt something that won't pay off for a century. The fourth reason is legacy. There is something in the human disposition that wants to contribute to things that will still matter long after the individual is gone. The people who first crossed the Pacific in outrigger canoes didn't know what they'd find. The people who pushed into unmapped continents didn't have satellite imagery. They went because going was what they did, because whatever they found would still be there after they were gone. An interstellar mission is the extreme version of that impulse, a contribution not to the next generation but to the next 100 generations. Now here's where it gets genuinely difficult. The counterarguments are not weak. The resources required to build an interstellar spacecraft, even a small, unmanned probe at a significant fraction of light speed, are staggering. That money, that engineering talent, those decades of institutional focus could be redirected toward problems that are killing people right now. Malaria, clean water, antibiotic resistance, climate adaptation. These are not hypothetical future problems. They are present, concrete, and solvable with things we already know how to do. There is a real moral argument that spending civilizational resources on a journey whose scientific results won't arrive for decades, if they arrive at all, while people are dying from preventable diseases, is a choice that requires serious justification. The second counterargument is probability. We don't actually know that Proxima b has anything worth finding. It could be an airless, radiation-blasted rock with no story to tell. The probability of finding life is unknown, which means the expected value of the mission is genuinely uncertain. You can't justify the sacrifice by pointing to a guaranteed return. You're betting an enormous cost against an outcome that might be nothing. And the third counterargument is the one that lands hardest on a human level. The people who go won't come back. They will spend the rest of their lives in a metal structure, cut off from everyone they loved, watching Earth recede into the background of history. Their children, if they have them, will grow up having never seen a natural sky. The crew members who die en route won't see the destination. The ones who arrive will be old, if they arrive at all. You are asking human beings to make an irreversible sacrifice for a mission whose outcome they may not live to see resolved. Both sides of this are serious. Neither can be waved away. What we can say is that throughout history, when the question has been posed in this form, here is something genuinely dangerous, genuinely uncertain with no guaranteed return. There have always been people who said yes, not because the math worked out in their favor, not because they were certain of success, but because the question on the other side of the journey was worth the asking. And despite the cost and the fear and the very real possibility that after 42 years you'd find a lifeless rock, people would still volunteer. That tells you something about what we are. The next time you're in the southern hemisphere, or you look up a photograph of the southern night sky, there's a bright point of light near the Southern Cross that represents the Alpha Centauri system, and somewhere near it, too faint to see, is Proxima Centauri. That bright point is actually two stars at once, Alpha Centauri A and B, so close together in the sky that human eyes can't separate them without a telescope. They look like one star, a single steady point of light sitting in the southern sky, a little brighter than most of what's around it. The light hitting your eye right now left that system over 4 years ago. Whatever was happening there in that moment, a flare erupting from Proxima's surface, a storm circling the terminator of Proxima b, you're only seeing it now. Here's what most people don't stop to consider when they look at a star. That system isn't standing still. Proxima Centauri has held the title of our nearest stellar neighbor for roughly 32,000 years. That's the entire span of modern human history, and then some. Cave paintings, agriculture, the rise of every civilization we've ever built, all of it happened inside that window. And it has about 25,000 years left before the gravitational geometry of the Alpha Centauri system shifts enough that Alpha Centauri A and B trade the nearest star title back and forth between them on a cycle of roughly 80 years. The universe doesn't hold still for us. The map of our stellar neighborhood is in slow, constant motion. That's not a minor detail. It means the night sky you're looking at is a snapshot. The stars will rearrange themselves on timescales that dwarf recorded history, and the thing we call our nearest star will eventually stop being the nearest star. Proxima Centauri is a neighbor in the way that a building 4 miles away is a neighbor. Technically accurate, profoundly unhelpful if you need to borrow something. Here's where things get genuinely strange, though. We know all of this. We know the distance to 4 decimal places. We know the mass of Proxima b to within a fraction of an Earth mass. We know the orbital period, 11.2 days, with extraordinary precision. We know the star's flare cycle. We know the spectrum of light it emits. We know how far away it will be from us in 10,000 years. We know more about a planet orbiting a star 25 trillion miles away than ancient navigators knew about land masses that existed on their own planet, separated from them by a few thousand miles of ocean. And yet it is completely, practically unreachable. Right now, with anything we've built or anything we're close to building, that gap between knowing and reaching is one of the genuinely unsettling features of our moment in history. We have built instruments sensitive enough to detect the gravitational wobble a planet the mass of 1/4 Earth imparts on a star 4.24 light-years away. We've done that from the surface of this planet without leaving. And we cannot send a probe that would arrive in any human lifetime with technology anywhere near what currently exists. Knowing and going are separated by an engineering gulf that spans multiple generations at minimum and possibly much longer. There's something worth sitting with in that image. You look up at that point of light in the southern sky, or you find a photograph of it, and what you're looking at is 4 years of distance traveled by photons moving at 300,000 kilometers per second. That's the minimum the universe requires just to tell you the star exists. Any signal you sent back would take another 4 years to arrive. If you wanted to physically go there in any meaningful way, you'd need a propulsion technology that hasn't been invented, sustained for decades, inside a spacecraft that doesn't exist yet, carrying people who haven't been born. And that's the nearest one. That's the closest thing on the map outside our own solar system. There are roughly 400 billion stars in the Milky Way. Proxima Centauri is the one immediately next door, 4.24 light-years away. And the honest reality of reaching it is that it would be one of the most technically demanding and psychologically brutal undertakings our species has ever attempted. Every star beyond it is farther. Most are enormously farther. The second nearest star system is Barnard's star at 5.96 light-years. From there, the distances grow quickly and they never come back down. The light from Alpha Centauri reaches the southern sky and looks to a naked eye like a single bright star near the Southern Cross. Calm, unchanging, close enough to have a name most people recognize. It has planets. One of them orbits in what might be a habitable zone. We don't know if it has an atmosphere. We don't know what its surface looks like. We don't know if anything has ever lived there. We don't know, and we can't go look. That light is 25 trillion miles old when it reaches you. It comes from a star we cannot reach, and it's the closest thing the universe has offered us, which should tell you something about how seriously the cosmos takes our desire to explore it.